The SpaceX Starship represents humanity's greatest opportunity to achieve a manned landing on Mars within your lifetime. What makes the Starship exceptionally qualified for this mission is, naturally, its remarkable power output. There's no question that a future iteration of Starship will possess more than sufficient capability to transport both astronauts and enormous quantities of cargo toward Mars. Ascending into space is one challenge. But what about the return descent onto the Martian terrain? We're discussing the most complex operation of the entire mission, the critical moment that determines success or failure, and there's far more complexity in solving it than you might initially assume. This is the process by which the SpaceX Starship will execute a Mars landing. Let's clarify immediately that we aren't all aerospace engineers or physics experts. I'm certainly not either of those professionals. Fortunately, we don't need to possess genius-level intellect to grasp the fundamental concepts underlying interplanetary navigation. Therefore, we're going to maintain everything at a highly approachable level. Before we can discuss Mars landing procedures, we must understand how the Starship reached that destination initially. The principle we must always keep in mind regarding space travel is that everything exists in perpetual motion, and within a solar system's framework, everything moves in orbital paths around the Sun. We're presently trapped within the Sun's gravitational influence, and the sole factor preventing us from descending deeper is Earth's orbital velocity, which measures approximately 30 kilometers per second. That's our current speed as we trace a massive circular path around a star, completing one revolution every 365 days. Mars sits at a greater distance from the Sun compared to Earth, indicating it hasn't descended as deeply into the gravitational well as our planet has, and consequently, Mars can maintain a slower orbital velocity without falling inward. Thus, Mars completes its solar orbit at roughly 24 kilometers per second. Now, if we wish to depart Earth aboard a spacecraft and investigate the planets, we'll transform into another object revolving within the Sun's gravitational well, and just like Earth itself, if we were to reduce our orbital velocity, we would begin descending into that gravitational well. This will alter our trajectory in the direction of an inner world like Venus. And through identical mechanics, if our spacecraft begins traveling faster than Earth, we will ascend the gravitational well, directing our orbit toward an outer world like Mars. Therefore, traversing the solar system fundamentally involves modifying your velocity relative to your point of origin. The technical terminology we employ to describe this concept is delta V, where delta signifies change and V represents velocity. We conventionally measure delta V in kilometers per second. So if Earth is traveling at 30 kilometers per second and you accelerate your spacecraft to 31 kilometers per second, you've achieved a delta V of 1. By identical logic, if you decelerate your spacecraft relative to Earth and travel at 29 kilometers per second, you've also achieved a delta V of 1. And yet, if you launch from Earth's surface at 1 kilometer per second, you won't begin ascending through the solar system. You won't rise above Earth's surface because gravitational force and atmospheric resistance are restraining you. These natural phenomena will influence the quantity of delta V necessary to maneuver the spacecraft. This explains why departing from Earth's surface to reach outer space is so challenging. The delta V necessary to attain a standard low Earth orbit will be approximately 9.4 kilometers per second. That represents a substantial amount of acceleration, and that's why our Starship requires the enormous power of the Super Heavy booster during launch. This also explains why the Starship must pause for a refueling operation in Earth orbit before it can proceed toward Mars, because we're going to require significantly more delta V to complete this voyage. To modify velocity, we need propulsion systems, and propulsion systems require fuel. The benefit of refueling in orbit is that it establishes our starting point anew. From this position, we only need an additional 9.5 kilometers per second of delta V to reach Mars's surface, essentially equivalent to the change required merely to escape Earth's atmosphere. However, there will be a significant difference in the strategy we employ for the mission's next phase, because while escaping Earth was entirely about accelerating, landing on Mars is going to demand extensive deceleration, and this can prove equally difficult to accomplish. A completely fueled Starship in low Earth orbit is projected to possess sufficient thrust for somewhere between 6 and 7 kilometers per second of delta V. This obviously falls somewhat short of our 9.5 kilometers per second needed to reach Mars. But that's acceptable because the identical forces that made escaping Earth's atmosphere so difficult, gravity and aerodynamic resistance, are going to function to our benefit when we approach for a landing, effectively amplifying the delta-V capability of our Starship. So here's how the sequence will unfold. Okay, we're in orbit around Earth, but even several hundred kilometers above the surface, we remain firmly caught within Earth's gravitational well. The only factor keeping us aloft right now is velocity. If the Starship were to decelerate at all, it would begin falling back toward Earth. By that identical logic, if we perform the opposite and accelerate, then we will continue ascending into space. Because we're still so near to Earth, we need substantial delta-V to counteract gravity. The ship must accelerate by 2.44 kilometers per second just to reach the altitude of geostationary orbit. Another 0.68 brings us to the Moon's altitude. Up here, we're finally at the edge of Earth's gravitational well. The force of gravity is infinite, but the strength of attraction diminishes relatively rapidly as you travel farther away. Now all we need is another 0.9 kilometers per second of velocity to escape Earth's influence entirely. From this location, floating in the vacuum of space far beyond the Moon, we only require 0.39 meters per second of delta-V to achieve our Earth-to-Mars transfer velocity. This second phase of the journey has consumed 3.6 kilometers per second of delta-V, which is at minimum half of the potential energy in our Starship, if not greater. And that means we lack sufficient fuel remaining to successfully land on Mars using engines alone. And here arrives the problem we must solve. All of the velocity we obtain to escape Earth's atmosphere and gravitational well has us traveling around the Sun at a considerably higher speed than Earth, which was already traveling at 30 kilometers per second to begin with. The planet Mars, conversely, is orbiting at a speed of merely 24 kilometers per second. So we're moving substantially faster than our destination planet, which means we're going to overshoot Mars and end up stranded somewhere in the asteroid belt unless we begin decelerating. After several months of coasting through the vacuum of space, we must execute our initial deceleration burn. After rotating the Starship around and getting the Raptor engines back to operating temperature, we must reduce 0.67 kilometers per second of velocity to become captured in Mars's gravitational well. This is the initial step in what's about to become an extremely turbulent ride. If we burn off another 0.34 kilometers per second of velocity, then we reach the altitude of the outer moon Deimos. 0.4 kilometers per second of additional delta-V brings us down to the inner moon Phobos. Here's where circumstances become genuinely complicated. By decelerating this much, we've already expended over 5 kilometers per second of the potential delta-V in our fuel reserves, and that leaves us with somewhere between 1 and 2 remaining. But we require at minimum another 4.5 kilometers per second of delta-V to safely reach the surface. In theory, this remains possible as long as we're highly strategic about how we utilize our final portion of fuel, and it's crucial to remember that everything from here onward is entirely speculative. This is our interpretation of the most logistically feasible Mars landing. If we want to preserve as much fuel as possible for our landing burn, then we must take advantage of certain external forces to slow our ship down to a reasonable velocity. Descending into a circular low Mars orbit would consume most of our remaining fuel, so we probably shouldn't execute that maneuver. In this scenario, we might be better served by inserting the ship into an elliptical orbit. So instead of flying in a circle, we're moving in an oval pattern with a low point, or periapsis, close to the planet, and a high point, or apoapsis, deeper out into space. By employing this maneuver, we can begin to exploit both aerodynamic resistance and Mars's gravity to help us decelerate. The Martian atmosphere is still exceptionally thin, but will accept any assistance available. We can lower the periapsis of our orbit down to the point where the ship actually penetrates into the upper atmosphere of the planet. By executing this very carefully, we can actually encounter some atmospheric resistance and lose a small quantity of velocity before getting flung back out to our apoapsis, where if we've performed this correctly, Mars's gravity will pull us back in to repeat the process once more. Every time we penetrate into the atmosphere, we gain slightly more of that precious delta-V, bringing us closer to the velocity we need for a gentle touchdown on the planet's surface. But we can't maintain this maneuver indefinitely. Eventually, we must transition from a shallow penetration to a full-scale dive through the Martian atmosphere. It's actually quite difficult to achieve a landing trajectory for Mars because the planet is only approximately half the size of Earth. That means the angle of attack required to get down below the sky is considerably steep. This means you need substantial energy pushing the vehicle downward to prevent it from skipping off and shooting back up into space again. We want to conserve our engines until the final possible moment. So that force to push the ship down deeper into the atmosphere must come from another source. This is why the original SpaceX design for an interplanetary transport system in 2016 featured an aerodynamic lifting body in the upper stage. Starship is much smaller than its predecessor, so it doesn't require as much aerodynamic force, but the methodology remains essentially the same. On its final approach, Starship is actually going to rotate over and enter the atmosphere inverted. So that's with the belly and tail directed upward and the nose directed downward. This way, the lift generated by the body is going to push the vehicle toward the surface at a steeper angle to achieve entry. We're also going to begin losing substantial velocity thanks to aerodynamic resistance. Once the angle of attack is established, the Starship is going to rotate around into the more conventional belly flop maneuver that we've witnessed on Earth. This is entirely about generating the maximum amount of drag that is physically achievable and reducing the velocity. But this force can only accomplish so much. The maximum speed of a free fall is something we call terminal velocity. Imagine you jump into a bottomless pit. Your body will accelerate as you descend up until a certain point when the drag and buoyancy of your body equalizes with the force of gravity and your speed becomes constant. One method by which we circumvent terminal velocity is by deploying a parachute. This dramatically increases drag and reduces our terminal velocity. Starship isn't going to employ parachutes, so there's going to arrive a point where the aerodynamic resistance of the vehicle has accomplished all that it's going to accomplish, and we reach terminal velocity. Due to the thinner atmosphere, terminal velocity on Mars is approximately 5 times faster than on Earth. In other words, that means you only achieve 1/5 of the delta V accomplished by belly flopping through the air on Mars, compared to what we've already witnessed Starship do on Earth, which means it's going to require more engine power to land on Mars than it does on Earth. This is why fuel is such a critical concern here. Assuming everything up until this point has proceeded correctly, the Starship's engines will ignite one final time and rotate the tail toward the surface, at which point the fuel in the rocket's header tanks will provide precisely enough delta V to bring our ship perfectly synchronized with Mars's surface, and we touch down gently. Now, that's an extensive list of things that must go right, and there is zero margin for error. You either achieve 100% on the exam or you perish. So by understanding all of that, we can appreciate that landing on Mars is going to be incredibly challenging in a massive vehicle like the Starship. It's much easier for NASA to land smaller and lighter vehicles on Mars, because the potential delta V of your fuel is determined by the mass of the vehicle and the efficiency of the engine. So 1 pound of fuel accomplishes more change in velocity for a lighter ship than it does for a heavier ship, and there is a constraint on the amount of fuel we can transport to Mars. Starship would be considerably easier to land on Mars if it were lighter, but SpaceX needs it to be so enormous to accomplish the objective that Elon Musk has established, which is constructing a self-sustaining city of 1 million people on Mars. SpaceX is working diligently on increasing the delta V of the Starship. They want to make Starship V2 longer with larger fuel tanks, while also making it lighter simultaneously and adding 3 more Raptor vacuum engines. The third version of the Raptor is currently in development and will probably offer higher efficiency and therefore more delta V capability. Now, there are other more long-term solutions as well. Remember Mars's outer moon Deimos? The delta V required to travel from low Earth orbit to the orbit of Deimos is only around 5.3 kilometers per second. That's far more manageable. And imagine if you could construct an outpost or a Mars gateway at the orbit of Deimos. Now we have the potential to refuel the ship so that it can make the most difficult part of the journey with more than adequate delta V to spare. This provides you a margin of error that would increase the safety of a Mars landing by orders of magnitude. So yes, landing a fully loaded Starship on Mars is going to be logistically insane. This is one of those situations where SpaceX won't know anything with certainty until they attempt it. We've witnessed this twice now with just launching the Starship, and both times it exploded in mid-air. Learning to land on Mars is more than likely going to be a similar experience. They are much more likely to fail before they succeed. They could fail multiple times. It's going to require a spectacular amount of determination to make this work, to not surrender, and probably more than many people are genuinely prepared for. And then eventually we attempt to do this with people on board, and calling this ambitious seems like an incredible understatement.